And it turns out when you have a lot of density, like the air around us is dense, not much happens. And that's what you're seeing now. But as we start to get lower and lower density, so there's less and less particles in here, something magical will happen. Let's see our little vacuum gauge, and there we go. So you see a little glow. That's pretty neat. So what's actually happening there is that the electrons are separating and recombining with the nucleus. And every time they do that, they emit a little packet of light in the visible spectrum so we can see it. So what you're seeing is we actually have electrons and we have ions, they're flowing together. Sometimes they rip off, sometimes they go back on. It's kind of this amazing sort of process that happens. So the point is what you can see is charged. It has an electric charge to it. Okay? So one of the ways we can prove that it's a plasma, meaning it has charge, it's not just a neutral gas, is we can actually push and pull it with magnets. Okay? So do we have a volunteer? We need a strong volunteer who wants to actually
Kai,
push the plasma.
Come on, Kai. You're
Okay.
strong.
So what's inside this tube is about 1 billion times less dense than solid stuff, okay? But the way we push a plasma is not by pushing on it. The way we can push a charged thing is we can use a magnet. So fundamental physics will tell us if we have a moving charged particle and we put it near a magnet, it will deflect, okay? It's called the Lorentz force. It's a fundamental law in electrodynamics. So Kai, you are going to be our Lorentz. And if you come over here, this is a big magnet. I want you to just push the magnet close to the glass tube.
Oh.
Okay. Very cool. So you literally push this charged gas around with a magnet. Okay? So we can be dangerous. You can see we can actually move it. We can literally influence where it is. So I can push it away from me. I can set up all these incredibly complex interference patterns. It's really amazing. Okay?
Is that why the Northern Lights do that?
So that is our next question. So we have a plasma. Okay, a plasma is charged. I just demonstrated, and Kai, thank you for the help. We just proved that we can push and pull this plasma with magnets. Okay. Now these are when we say magnets, most people associate magnets with with regular magnets. Put them on your refrigerator. You put the kids' artwork up. Looks good. But of course, we can also make electromagnets. So we can actually take a current, we can run it around a loop of wire, and that's going to make a magnetic field. Okay? So what we're going to do is actually run current around a wire with our power supply.
Thumbs up.
Okay?
Oh, yeah.
So if you notice in between these magnets, the column is narrower. Everybody knows that? So I'll turn the magnets off. Pops back. Narrower. Pops back. So right now, this plasma is hitting the walls of the container. Okay? But when I squeeze it with magnets, you can see it's actually well isolated from the walls. Okay? And it turns out when I isolate the plasma from the walls, heat can't actually escape from that plasma to the walls by conduction. Okay? So if you squint a little bit, you might convince yourself the color is a little different. Okay?
Brighter.
It's a little brighter, maybe a little more yellowish, particularly in here. And that's because the temperature has changed ever so slightly because it can't actually conduct its heat away to the wall. Okay? So this is kind of the way to think about what magnets do is they're insulators. They literally squeeze this plasma and they insulate the plasma from the wall. Okay?
So then if you use the magnets, then are you less concerned about the material that the wall is because they can't
Exactly
touch
right.
it, right?
Exactly. So we isolate this plasma from the wall. And the way to think about the magnetic field, it's like the insulation in your house, right? The higher the R value of the insulation in your house, the more efficient your heater is, right? A little bit of heat goes a long way, and it's exactly the same way in a fusion device, okay? So now, exactly to your point, if this was a real fusion machine, this plasma might be at 100 million degrees. But if we work really, really hard and we arrange a bunch of magnets correctly, we can actually hold this 100 million degree thing without touching a material in an ideal world. And that drastically lowers the influence of the plasma on the material. So that's a big help, right? So right off the bat, we actually can hold a plasma away from the materials.
Does the glass feel kind of warm?
It feels a little warm.
And does it feel less warm in the middle?
Yeah, not that much. It's not going to be that big. And the biggest heat is actually from these copper coils, which are resistive. But one thing you notice is that we squeeze it in this direction, but it's kind of free to flow this way. So, quite a while ago, they came up with a clever trick. Well, what do? Why don't we make a bunch of magnets? Let's bend it into a circle, to a donut or a torus. That's kind of this fun student project, right? Bunch of magnets. Inside would be a circular plasma. That's why most of the plasma machines you see are circular, because we use the magnets to hold the plasma away from the walls, and the plasma just zips around quite happily at 100 million degrees, burning hydrogen, turning that hydrogen into energy that we can use if we've done our homework correctly. Okay? So that's a pretty nice little demonstration of sort of exactly what we do in fusion and kind of why it works. So I think when I said, we put a star on Earth, how the heck do we do that? We put it in a magnetic bottle, and it's quite happy to just sit there and be held. We can add energy to it, and eventually we can start to extract energy from it. Okay? So the analogy I always use with fusion is if you think about a campfire, right? So most of us have built a fire, tried to light it at some point, right? And it doesn't work very well to light wet logs on fire, and that's because we're not getting the temperature high enough. We're not driving the chemical reactions that make heat. And if we try to, let's say just burn a log, all that heat just escapes. It's really hard to burn a log. You've probably all been taught you have to build a little pyramid structure. And the exact same thing is true in fusion. So what Dennis was talking about earlier is exactly the same thing. We need fuel. We need to get its temperature up. But more importantly, we need to arrange it in such a way that any temperature we generate sticks around. It's actually, driving the reactions that are making fusion possible. And so that's why we have these funny magnets and these funny configurations. Is we want to generate heat from fusion, and we want to trap it in the fusion. So just like a fire, it ignites and it just burns. Okay. So like a fire, you don't have to add fuel to it. I mean, you do eventually, right? You have to put an extra log on, but you're basically changing, the chemical pattern of that fuel, and you're releasing energy. Fusion's doing the same thing. It's just